Okay, so we've looked at the confidence interval to estimate a population mean. Let's see what happens when we want to estimate a population proportion. First of all, we'll just refresh our memory. The confidence interval is given by the point estimate plus or minus some multiple of the standard error. And in the case of a confidence interval for a population mean, we had an expression that looked like this. That confidence interval was going to be x bar plus or minus t times s over the square root of n. Now, in the case of a population proportion, we want to estimate the population proportion. Same idea. We have a point estimate plus or minus some multiple of the standard error. The question is, what's our point estimate, what's our multiple, and what's our standard error? Well, think of it this way. What proportion of a population meets a certain criteria or has some certain property? What proportion of the population agrees with some president's environmental policy? Anything of that sort. What proportion of a batch that we sample from a production line is defective? A number of questions like this we could be interested in investigating. What proportion of the overall market prefers a particular brand? If we're investigating things like market share and we want to estimate that from some sample. Well, we tend to use the expression what I call p hat here as our estimate for our population proportion. So instead of x bar, the symbol you'll see is p hat, p with a little upside down v on top of it. And for large sample sizes, a sampling distribution has the following criteria. That expected value, the mean of this sampling distribution, is going to fall right at our population proportion. So remember, we're trying to find the characteristics of our sampling distribution of our that's made up of all the possible sample proportions that we could come up with. Now we're saying the expected value or the mean of that distribution falls right at the population proportion. This is similar to the case for the sampling distribution of sample means. Remember, the central limit theorem told us that the mean of that distribution would fall exactly at mu. So here we are with a similar situation. Secondly, we find that the standard error has this mathematical formula. So instead of s over the square root of n or sigma over the square root of n that we would have used for the case of the sampling distribution of a sample means, here the standard error takes on a different expression, but it means the same thing. It's the standard deviation of the sampling distribution, but the expression for it is going to be the square root of my sample proportion multiplied by 1 minus the sample proportion, all divided by n, and then the square root of that entire expression. And let me pause here for a moment and say that both of these expressions, okay, the expected value or the mean of my sampling distribution and the formula for the standard error of the sampling distribution really come from something we understand very well. They actually derive from the binomial distribution. And if you think of it from the standpoint of us taking a certain sample size, our sampling distribution is made up of samples all of the same size. So we're taking various samples all of the same size. Each of our criteria, each of our elements in our sample, either meets the criteria or does not meet the criteria. It's at one of two possible outcomes, again, like the binomial distribution. And then we know that there is somewhere out there this overarching population proportion that does exist. It's the thing we're trying to estimate, but we know that it does exist, and that's the equivalent of our probability of success, the probability that any one element that we choose would meet the criteria or not. So this actually has all the elements of a binomial distribution, and if you have the time and the inclination, you can actually go back and see how these would fall out of what we know of the expressions for the expected value and the standard deviation of a binomial distribution. But that's where these come from. And again, it's really not that complicated given what we know to derive them, but we don't need to derive them. We can just take these expressions as a given and then just plug them in to do our calculations. So we have our point estimate p hat. We have our standard error expression here. And the question is, what do we need to use as our multiple? And well, I'll tell you what it is. We're going to use the z value, okay? The reason we're going to use the z value is somewhat interesting, because you might ask, well, why is it that we're using the z value here, whereas in the case of the mean we had to use the t value? And it has to do with the fact that we're not making that substitution of an unbiased estimator, okay? As it turns out, in our actual expression for standard error, this is not p hat, but it's really the population proportion that should be in this expression. And we're substituting p hat for our population proportion, but it turns out that p hat, our sample proportion, is an unbiased estimator for population proportion. So once we make that substitution, we actually do not have to suffer that penalty of losing a degree of freedom, and we're able to use our z multiple. Again, we can show all of this, but we can also just take it as a given. And that's what we'll do for our purposes. So in this case, so remember, in the case of a confidence interval for a population proportion, we do not need to use the t distribution, the student t distribution, in place of the z distribution. We can go ahead and use the z value. So we're going to want to remember that norms inverse function that we talked about earlier on to get our z multiple. Norms inverse of confidence level plus alpha over 2. Okay, so you can go back and look that up if you need to refresh your memory, but that's what we need to use in this case. Now, one of the things we do have to do is something called a validity check, and it has to do with the fact that we said we're going to model the sampling distribution based on a binomial distribution. But as we know, the binomial distribution is not always symmetric. Okay, depending on whether probability of success is very close to 1 or very close to 0, or whether it happens to be in the middle, close to 0.5, the distribution could be skewed very heavily to the left or to the right, or it could be symmetric. And it turns out what this validity check does for us is it allows us to just go back after we've come up with our estimates for population proportion. It allows us to go back and check and say, hey, given this estimate for population proportion, which is the equivalent, remember, of our probability of success, is my distribution sufficiently symmetric that I can legitimately model it with the standard normal distribution? And it turns out that there's a combination of factors that have to come into play. And it's a combination of the sample size. Is our sample size large enough? And accompanying that is our probability of success, is our population proportion estimate sufficiently central, so sufficiently far away from the extremes of 0 or 1, that the distribution is normal enough to be modeled with the z distribution. So what we do is we take that sample size n, and we take each of our estimates for the boundaries of our confidence interval, the lower estimate and the upper estimate, and we're going to check those. We're going to multiply them together. So we're going to take our lower estimate and we're going to say n, sample size, times our lower estimate of our population proportion that comes out of the expression we just did, comes out of our confidence interval calculation. We're going to get an upper value and a lower value by using the plus or the minus in that expression. So our lower value, the one we get using the minus sign, we're going to multiply that by our sample size, and we're going to check to see if that product is greater than 5. Then we're going to take that sample size multiplied by 1 minus this lower estimate that I call P sub L here. And we're going to check to see, is that product greater than 5? And then we're going to repeat those same two expressions for the upper estimate. And if these conditions hold for the lower estimate and for the upper estimate, we can assume they're going to hold for everything in between, because those are going to be further away from the extremes. All right, now what about this 5? Where does 5 come from? Is it tied to the concept of a 95% confidence interval? No. Just like our empirical rules, this came from many, many observations of binomial distributions. And people have found that if this product of n and p is greater than 5, and the product of n times 1 minus p is also greater than 5, then the binomial distribution is sufficiently symmetric that we can actually model it effectively while using the normal distribution. So again, this is just something we're going to know, but it's an important check for us to do. So once we find our PL, our lower limit of our confidence interval for the proportion, and our P sub U, our upper limit of the confidence interval for the proportion, we know our sample size, so we're just going to plug those in and evaluate these 4 expressions. And if all 5 of these products are greater than 5, then we should be, and we know we're in good shape. That we know that it was okay for us to use the Z distribution and everything is fine. What if one of them is below 5? And usually it'll only be one of them that's small. So the lowest of these, if it's below 5, what do we do? Well, the easiest thing is to go back and take another sample with a larger sample size, because in any of these expressions, if we increase the sample size, it's going to increase the product. And if we know which one of these is the one that's below 5, we can actually calculate and see, well, okay, how big a sample size do I need in order to ensure that it's going to be sufficiently symmetric? So we have some information to go on. But it's important to do this check just to make sure that we're heading down the right track with our expression. All right, so in Excel, we've got some data set and we want to use it to calculate the confidence interval for the proportion that meets some criteria. First of all, we need to determine from our data set how many observations meet the criteria. And we can use an if function or a count if function. We can actually use a pivot table, a number of different ways we can do this in Excel. And then we calculate the sample proportion by saying, well, how many observations met the criteria divided by the sample size. So this gives us our p hat, our point estimate. And then we're going to go ahead and use our norms inverse function to find our z value, depending on whatever the confidence level is. And we can just evaluate the standard error function using the expression a few slides back, right? Our p hat times 1 minus p hat, all divided by sample size, and then the square root of that whole expression. That's going to be our standard error. So we have all the elements of that. So we can just build those together and calculate the upper and lower limits of our confidence interval by using either the plus sign or the minus sign in that confidence interval expression. And then finally, we go back using each of those upper and lower estimates and we do our validity check. We check the product of n times PL, n times PU, n times 1 minus PL, and n times 1 minus PU, and we make sure all of those are greater than 5. So once we've done that and we've done our validity check, then we can say, yes, we are confident to whatever degree we are confident, given our confidence level, that the population proportion will fall between this value and this value, our P lower and P upper, respectively.